Okay, hi everyone. So in this video, we're going to be looking at solving a few problems with respect to the topology on metric spaces. So in this first question, we are given this theorem that is basically talks about when two metrics are said to be equivalent. So two metrics, row 1 and row 2, on a set X are said to be equivalent if or topologically equivalent if and only if given any element in the metric space X and any open sphere with respect to the metric row 1, it will contain another open sphere, but this second open sphere is now of a different radius and with respect to the metric row 2. Okay, and in a similar way, we could have, for example, so let's say it's over here, that is given any x in x and any radius, I could find two positive real numbers, R1 and R2, such that the open sphere with respect to row 1 is contained in an open sphere with respect to row 2. And any open sphere with respect to row 1 is contained in, any open sphere with respect to row 2 is contained in an open sphere with respect to row 1. And any open sphere with respect to row 1 is contained in an open sphere with respect to row 2. In other words, what this saying is that uh, two metrics are said to be equivalent if in any open set with respect to one metric, you could find an open set with respect to the other metric and vice versa. So what I want to do now is, let's say you have a metric space X comma D, and we define on this metric space another metric, let's call it mu, where mu is equal to, so D is one metric and mu is the other metric. So in this definition, in this theorem, row 1 will be D and row 2 will be mu. And this new metric mu is just the value of the metric D divided by 1 plus D. And I want to use this theorem to prove that these two metrics are equivalent. So just a side note, this metric mu is very important because I'll put it aside. This metric mu is very important because let's say the metric space XD is unbounded. So given any metric space X comma D, so one thing you could do, we don't have to show it here, but one thing you can do is that the mapping or the map given by this map here, mu of x, y, right? You could prove that this map is also a metric, right? It basically exploits the fact that D is a metric and the property is that mu is a metric. So you have to check if mu is positive definite, if mu is symmetric, if mu satisfies triangle inequality, all those things. And you could do that. So this map mu for all x and y and x is also a metric on this space X. Not only is this metric mu, or let's just say not only is this map also a metric on the space X, is that this metric, so in addition, this metric space now X with respect to mu is a bounded metric space, is bounded. Okay, and the reason is because if you look at mu, right? So mu is D over 1 plus D. So we know, for example, remember D of x comma y is always bigger than or equal to 0, right? So for the case where D is equal to 0, that is when X is equal to Y. So when D is equal to 0, you get, if you look at what mu is, you will get mu is equal to 0. So D is equal to 0 implies mu is equal to 0. For D of X comma Y equal to 0, this implies that mu of X comma Y is equal to 0, okay? Otherwise, if D of X comma Y is strictly bigger than 0, 1 plus D of X comma Y is strictly bigger than D of X comma Y. And from this, we could get, so just take the left-hand side over to the right-hand side, and we will get, so maybe I should put this as strictly bigger than 0. And if you divide through by 1 plus D X comma Y, you get 1 is bigger than D X comma Y all over 1 plus D X comma Y bigger than 0. Okay, and this guy here is just mu. Therefore, 0 is less than or equal, right? Because we know when D is equal to 0, mu is equal to 0. So 0 is always less than or equal to mu of xy, and mu of x comma y is always strictly less than 1. And this holds for all x comma y in the space X. In other words, the metric space x comma mu is bounded. Okay, so this is a metric that you could put on any space. So it doesn't matter if the original metric space x comma d was bounded or not. This new metric space that you get with this metric mu will always be bounded. Okay, so that's just an aside. Right? Didn't not prove that. So what we want to do now is show that not only is this metric mu converts a metric space into a bounded metric space, but the topology that it also puts on this metric space is exactly the same as the original topology. Okay, so prove, I want to prove, so we show that mu and d are equivalent metrics. As follows. Okay, so the strategy is I'm going to take an open ball or open sphere with respect to one of these metrics and show that I could find an open ball or open sphere with respect to the other metric inside that first one. Okay, so let me take an open sphere or open ball centered at X. Right, so X, we could say let X be any point in X. I'm going to take the open sphere around X of radius R, where R is some positive number. Okay, be any. So now I have to tell you this is an open sphere with respect to the D metric. So the metric, I'll put it as a superscript. Be any open sphere with respect to the D metric. Okay. And S mu R prime X be any open sphere with respect to the mu metric, okay? Because we have two metrics here. So I have one open sphere with respect to the D metric and one open sphere with respect to the mu metric. These two open spheres, notice they are both centered around the same point X. Okay. But the radius for the one with respect to the mu metric is different. It's r prime. So in these proofs, we just need to choose r prime in a specific way. In terms of this example, the way to choose r prime is given like this, where r prime, in this case, I'm going to choose r prime to be, so we are given r. So I'm going to choose r prime to be r over 1 plus r. Okay, and of course, this is bigger than 0. So required to show, what do I want to show? I want to show that inside this open sphere, which is respect to the D metric, center that X of radius r inside this guy, I could find an open sphere with respect to the mu metric of some other radius. Okay. And notice that r prime, okay, we'll get into that. So I want to show this, so maybe we could call this star 1. Okay. So how to show one set is a subset of the other? I let y be in the first set, so that's my open sphere with respect to the mu metric. Okay. So if y is in this open sphere, that means that the distance, so the distance with respect to the mu metric between the center and y is less than r prime. Okay, that's just the definition of being in an open sphere. And now all I have to do is remember what is mu. Mu by definition is d of xy over 1 plus d of xy, right? That is what mu is by definition. And how did I define r prime? R prime, I define that to be r over 1 plus r. Okay, so all I did there was I just sub in what was mu, what was r prime. Now I'm just going to simplify things a bit. So from here, I could get d of x comma y plus, so I'm just going to cross multiplying because they are all positive numbers, plus r of d of x comma y is less than r plus r d of x comma y. Okay. And so from here, okay, so I guess I should have specified from the start that y and x are different points, but it's understood because if for the case where y is equal to x, then obviously if y is equal to x and x is in the sphere centered at x with respect to the D metric, then the subset relation will obviously hold. So this subset relation is obviously true for the point y equal x. So I'm taking y not equal x. And since y is not equal x, d of x comma y is not equal to 0. So I can remove it from both sides, and I simply get d of xy is less than r. So this is telling me that the distance between the points x and y with respect to the D metric is within radius r. In other words, y belongs to the open sphere or open ball with respect to the D metric centered at x of radius r. Okay, and that's what I want you to show. So yeah, so hence we have star 1. So I've proven that that if you give me an open sphere centered at x with respect to the D metric of some radius r, I could find an open sphere centered at same x with respect to the mu metric of radius r prime, right? And how do you choose what is the relation between r and r prime? Well, r prime is equal to r over 1 plus r, okay? And now what we have to do is the same thing, but the converse of it, okay? So now we will show the converse of this, which is if you give me an open sphere with respect to the mu metric centered at x of some radius r prime, I'm going to find an open sphere inside of it with respect to the d metric centered at the same point x of radius r. And of course, if I want to show the subset relation, I take a point in one set and show it in the other set. Of course, if that point is equal to x, the inclusion is obvious because x is contained in both open spheres. Okay, the center is always contained in that open sphere. So what I'm saying is I'm going to let y be not equal to x, so a point different from x, be in the open sphere with respect to the d metric of radius r, centered at x. Okay. Um, that's why we here. So now we'll show, and so I now need to give you the relationship between r and r prime. So in this case, we are given r prime, and take r to be equal to r prime over 1 minus r prime. Okay. Of course, if r prime is bigger than 1, then you take it to be 1. Okay. So take r to be this. What this implies, if y belongs to this set, that means that the distance between x and y with respect to the d metric is less than r, okay? And so now I need to solve, now I need to come over here and do a little calculation. I know that mu of x comma y is equal to d of x comma y over 1 plus d of x comma y. So I need to solve for d. Okay, so if you solve this for d, you'll see that d of x comma y is equal to mu of x comma y over 1 minus mu of x comma y. Okay, and I'm going to sub that in over here. So d of x comma y is mu over 1 minus mu. Okay, and r, I'm taking r to be r prime over 1 minus r prime. Right, so again, simplify this. So I get mu xy minus r prime mu xy less than r prime minus r prime mu of xy. Okay, and of course, all of this is the case where maybe I should say case when 0 is less than r prime is less than 1. Okay, and for the case where r prime is bigger than or equal to 1, I'll leave you to fill in that case. That's a one-line case. What to do? So fill in I'll let you think about what to do in that case. Fill in how to choose r if r prime is bigger than or equal to 1, right? I claim you take it to be equal to 1. Okay, so from here, we could simplify this down and we get mu of x comma y is strictly less than r prime. In other words, y belongs to the open sphere centered x with respect to the mu metric of radius r prime. Okay, so hence we have star 2. Okay, so what we did there was we showed that if you give me, so star 1 shows that if you give me any open sphere around x of any radius r with respect to the d metric, I could always find inside of it an open sphere of some radius r prime with respect to the mu metric. So the open spheres with respect to the mu metric, you could always find an open sphere like that inside an open sphere with respect to the d metric. That's what star 1 is showing. And star 2 is showing the converse of that. That if you give me an open sphere with respect to the mu metric of any radius, r prime, I could always find an open sphere with respect to the d metric inside of it. So maybe we could write a statement like that. Thus, we have shown that every d open sphere is in, well, not every d open sphere maybe contains, every d open sphere contains a mu open sphere. And conversely. Okay. So therefore, the metrics mu and d are equivalent by the stated term or by the given term. Okay, remember we were given a term in the beginning to work with. Right? So in this case, I didn't use this notation. The notation I was using was S row 2 R1 X. And this guy, I use the notation S row 1 R X. Okay, but it doesn't matter what notation you use. Okay, so that's it for that question. Okay, so in this question, we are given that XD is a metric space and Y is a separable and then subset of X. Show that X is also separable. So we just need to recall this definition. Recall. So dense means, so we say a subset, let's say A in X is dense in X if the closure of it is equal to the entire space. And so that's the first one. And what is separable? So we say that a set A is separable if it contains a countable dense subset. So maybe I should use, yeah, let me use Y. So is that Y is separable if it contains a countable dense subset, uh, A subset of Y. So that's what dense is and separable. So separable means you have a countable dense subset. Uh, so for this proof, we suppose Y is a separable and dense subset of X, is a separable and dense subset of X. So Y has both of these properties up here. So yeah, maybe maybe again I should use the letter Y just to be sure we're all consistent. So it's subset Y effect is dense in X if the closure of it is equal to X. Okay. So since Y is separable, well, the definition is right there, but let's write it back. So since Y is separable, it contains a countable dense subset. Let's call this guy A. Okay. So again, what does this mean? So all this means is that A, okay, is contained in Y, and of course Y is contained in X. And because A is a dense subset in Y, that means that the closure of A is equal to Y, right? Since Y is separable, it contains a countable dense subset. So A is dense in Y. So the closure of A is equal to Y. So I claim here, my claim is that this A, I claim that not only is the closure of A equal to Y, I claim that the closure of the same set A is actually equal to X. Okay, so as I claim, I claim that this set A is not only a countable dense subset of Y, but it is also a countable dense subset of X. And if I could show that, then of course X will be separable, because if you are separable, you have a countable dense subset. So in other words, this means that X is contained in A bar, okay? Because A bar is obviously contained in X. So I want to show that. Okay, so how to show this inclusion? Well, suppose X belongs to X. I want to show X is now in A bar. So remember what A bar is equal to? I'll write it here. A bar is the closure of A, which you can write as A union its limit points. So suppose X is in X. If X belongs to A, right, and A is always in closure, then we are done. Okay, so if X belongs to A, we're done. Nothing to prove. Otherwise, let's say X is not in A. Okay, so if X is not in A, I need to now show or argue why X must be a limit point of A, which means it will be an A bar. So otherwise, X is not in A. Now, since I know that Y is dense in X, right? We assume that to begin with. Since Y is a dense subset of X, so since Y is dense in X, so again, that means that the closure of y is equal to x. It means that given any epsilon bigger than 0, I could always find a point in y such that arbitrarily close to x, such that these 2 points are arbitrarily close together. And I'll take it to be epsilon over 2. Okay, so this idea that I'm using here is the idea behind what the property dense is trying to capture. So when one set is dense in another, it means that you could always find points of that set. In this case, it's y. So if I say y is dense in x, it means if you give me any point of x, I could always find some point of y arbitrarily close to that point x. Okay, so if you give me any radius epsilon, I could always find an element y belonging to the set y such that the distance between x and y is arbitrarily close. But I know that A is also dense in y, right? That's what my other assumption was. So also, since A is dense in y, so again, I'm going to apply that same result. Since A is dense in y, if you give me any point of y, I could always find that there exists a point in A such that this point is arbitrarily close to the guy in y, such that the distance between A and y is again arbitrarily close, and I'll take it to be epsilon over 2. Okay, so what if I work out what is the distance between x and a now? So the distance between x and a, so use the triangle inequality, is less than or equal to the distance of x to y plus the distance of y to a. Okay, and the distance of x to y I know is epsilon over 2, and the distance of a to y, which is the same as the distance of y to a, since the metric is symmetric, is epsilon over 2, which is epsilon. So what did we show? We've shown that x must be a limit point of A, right? Given any epsilon, I found a point x arbitrarily close to this point A. So hence, x is a limit point because this point x was not an element of A, right? Hence, x is a limit point of A, which means x belongs to the derived set of A, which is of course contained in the closure. So therefore, it follows that the closure of A is equal to x. And so A is dense in x. That's what the closure of A equal x means. A is dense in x, but A was countable. And A is countable. Okay, so X contains a countable dense subset. That is, X is separable. Okay, so in this proof, we just we utilize the fact that Y is dense in X and A is dense in Y. So right over here. A is dense in Y and Y is dense in X, right?